Hello everyone and welcome to the video on solving trig equations. Our skill objectives for this video are number 1, to solve trig equations by inspection. Number 2, solve trig equations using algebraic techniques. The third thing is solve trig equations using inverse functions. And number 4, solve trig equations using identities. In this video we'll use all of those. We'll do all of those, so you'll see examples of each one. Conceptual objectives: 1, understand that solving trig equations is similar to solving algebraic equations. And number 2, realize the goal is to find the values, notice in the parentheses the s, of the independent variable that make the equation true. In other words, when you solve, you want to find, you're going to be given an interval, you want to make sure that you find every number within that interval that will make the equation true. Now, when will we work on these ones? There are going to be two basic types of problems. The first one is going to be where they're going to solve over an interval, okay? And so they will actually express the interval in some way. It could be 0 to 2 pi, could be 0 degrees to 360 degrees. Those are the most common, but we could actually use any interval. In the book, you'll see things like from negative 2 pi to 0. We could also go from negative pi to pi. Or they could even go something like negative 2 pi to 2 pi. But that interval can be anything I want, okay? The other one that we have is where we have to solve over the real numbers. In other words, we're going to try to identify every place that makes a trig equation true. Now, this should right now cause you a little bit of concern because of the fact that you know trig equations are cyclical, and therefore, because they're cyclical, they repeat over time, and therefore, there actually are an infinite number of solutions. And so what we're going to do when we do this, because if we're solving it over the real numbers, it means we have to identify every solution. And so what we're going to do, you're going to see something that will come into play, and it's really going to be that what we're going to do to the solutions that we find, we're going to add the period. We're going to go through and we'll just take plus the period, whatever that period is, times n. And the phrase that we'll have after that is going to be where n is an integer. That is going to give us all solutions to that problem that will work out. So we want to keep that part in mind as we go through this, and we'll see an example of how we can apply that in the next couple slides. Here are a couple problems that we're going to use inspection to help us identify the solutions. Often when you see these are going to be problems where the trig function is going to equal a number, and that number is going to be something that appears on the unit circle. I'm not going to ask you to solve something by inspection that isn't already on the unit circle, because you can't give me the angle measures for anything other than the ones that you know off of that circle. So in this first one that we have right here is the cosine of x equals square root 2 over 2. And I want to find all the solutions on the interval from 0 to 2 pi. So what I'd like you to do is pause the video, and I want you to identify every value for x that has a cosine of positive square root 2 over 2. Okay, welcome back. On this one, you should have come up with, in this case, that x would be equal to, let me put in the pen, that x would be equal to pi over 4. That was one that has a positive square root 2 over 2, cosine of square root 2 over 2. And the other one happens to be when x equals 7 pi over 4. So those would be the two solutions that we have there. It's just really knowing that unit circle that's going to help you out with this. Now in the next one, it's a little bit different. In this case, what we have is a sign of 3x equals negative 1/2. And we want to find all the solutions from 0 to 2 pi. Now this is going to take a little bit more work to do, but it is something that we can accomplish. So the first thing I want you to do is when we do these, we have to identify what our angle is equal to. So I know the sine of 3x equals negative 1/2. So you want to go to your unit circle, identify the angles that have a sine value of negative 1/2. So pause the video and identify those. Welcome back. You should have found that the angles that have a sine value of -1/2 are 7 pi over 6 and 11 pi over 6. And so what I'm going to do is I'm going to let those angles, the 3x equals 7 pi over 6 and 3x equal 11 pi over 6. Now there is one other part that we have to do on this. In this case, I know the period of this sine function is 2 pi over 3. And so what I'm going to do is I'm going to add an integer multiple of my period. So in this case, for each one, I'm going to do plus 2 pi n over 3. The reason for that, again, is I am just adding on the period each time there. And what I can now say is if 3x equals 7 pi over 6, or anything in here where I put an integer in for n and I simplify that, or 11 pi over 6 plus this integer multiple of the period, I will actually get an angle whose sine value will be -1/2. Now keep in mind, our goal on this is always to solve for x. Right now I know what 3x is. I need to know what x is. And so what I'm going to do now to solve it for x is I'm going to go through and divide by 3, which is the same as multiplying by 1/3. And so when I do that, I will get that x equals 1/3 times 7 pi over 6 plus 2 pi n over 3. And x equals 1/3 times 11 pi over 6 plus 2 pi n over 3. Now distributing that in there, I get x equals 7 pi over 18 plus 2 pi n over 9, or x equals 11 pi over 18 plus 2 pi n over 9. Now what we need to do is we need to generate every value, every solution to this particular equation for all the values from 0 to 2 pi. So in other words, I need to find every number from between 0 and 2 pi that when I plug it in for x, I'm going to get the correct solution. And to do that, I'm going to use these two pieces. But what I'm going to do, what I'm going to want to do is make sure I get a common denominator. So that first piece is going to be x equals 7 pi over 18 plus 4 pi n over 18. And what I'm going to start by doing is I'm going to put in values for n, which will generate every solution on this that I can use to go through and plug in the solution. So in this problem, what I'm going to start by doing is I'm going to let, for this first piece, I'm going to let n equal 0. And when I do that, I'm going to get 7 pi over 18 plus 4 pi times 0 over 18 is 0. So I get 7 pi over 18. That's my first solution to this one. To get to the next one, I'm going to put 1 in for n. So I'm going to get 7 pi over 18 plus 4 pi over 18, which is going to give me 11 pi over 18. Now this one actually helps me out a little bit, because what I notice here is that this second value that I've generated, the second solution to this one, happens to be what would be the first solution in this second piece if I put 0 in for n. And so when that happens, what I know is that I can now generate every solution here by just plugging in integer values starting with 0 until I get something bigger than 2 pi in for n on that piece. If that wasn't the case, in other words, if I did not generate that first term, that first solution from that second piece, then I'd just have to do the same thing I'm doing with this one here. I'd start with n equals 0 and again keep generating values until I got something bigger than 2 pi in each one. But because of how this works out, I can just keep plugging in values of n into the first piece, and that will give me all my solutions. So the next one I'll put in as n equals 2. I'm always going to go up, n is always going to go up by 1. And when I do that, I'll get 7 pi over 18 plus 8 pi over 18, which is going to be 15 pi over 18. When I put n equals 3, I'll get 7 pi over 18 plus 12 pi over 18, which gives me 19 pi over 18. Now at this point, you're probably noticing that each time, each solution, I started with 7 pi over 18. I went up in the numerator, it was increased by 4 pi, went to 11 pi over 18. Again, up by 4 pi to 15 pi over 18 to 19 pi over 18. You can kind of see a pattern here that can help you generate the rest of the solutions. So I know that when I put n equals 4, I'm just going to increase that numerator by 4. So I'm going to get 23 pi over 18. When n equals 5, I'll go through and get 27 pi over 18. When n equals 6, I'm going to get 31 pi over 18. And when n equals 7, I'm going to get 35 pi over 18. Now you notice that 36 pi over 18 would be 2 pi, so if I try to go any further, I would end up I would have something that would be outside of the values that I'm looking to have my solutions be between 0 and 2 pi. So I know in this case that I ended up with 8 solutions. 7 pi over 18, 11 pi over 18, 15 pi over 18, 19 pi over 18, 23 pi over 18, 27 pi over 18, 31 pi over 18, and 35 pi over 18. Now keep in mind on this as well that this number here, the number that you see out in front there, the 3 in this case, if you start out, if you put into each piece, you know you're going to, at least if this pattern hadn't happened here where I had the 11 pi over 18, which would come from here, that I would end up putting the numbers from 0 to 3 into this piece, generating 4 solutions, and 0 to 3 in this piece, generating 4 solutions. This number here will always tell you how many solutions from each piece you're going to end up getting. So, or in this one more than that number. Let's take a look at another one. These ones are going to be all real numbers. Now, in these problems, this idea is still going to be the same. What I'm going to do is, on this first one, I have sine of x equals square root 3 over 2. I want to solve it for all real numbers, which means that I need to identify everything that is, plus that period, okay? And so what I'm going to do on this one is I look at that, and I know that the period in this is 2 pi, because there's the coefficient on the x is 1. So sine of x equals square root 3 over 2. I know that x is going to have to be the sine square root 3 over 2. That happens at pi over 3 plus my period 2 pi times n, where n is an integer. And then x equals, another place that it happens is 2 pi over 3 plus that 2 pi n, again, where n is an integer. And that's really the only difference I have in that particular problem. All right, now let's look at the second problem. Tangent of 2x equals -1, and we're going to do all real numbers. In this case, we'll do it in degrees. So we'll work with degrees. And because of the tangent, we know the period on tangent is, one way of looking, if you're in degrees, is going to be 180 degrees over b, which in this case is 2. So the period here is equal to 90 degrees. So that's what I have there. Now, to do this one, we need to identify this, and I want to solve it. So x, I know 2x, the tangent's -1. So I can say that 2x equals the angle that has a tangent of -1, one that you have, comes out to be at 135 degrees. So that should be 135 degrees. Now, because we want all real numbers, I need to do plus that 90 degrees times n. That will give me every angle that's going to be that will give me a tangent of -1 here. Of course, I do still have to solve it for x. To do that, I divide by 2. And so what I'll get is x equals 135 degrees divided by 2 plus 90 degrees times n over 2, which you can simplify that a little bit. Just say 135 degrees over 2 plus 45 degrees times n. And again, where n is an integer. And that will give us every value that will make that I can plug in for x that would make this equal to -1. The next thing we have is using algebra techniques. Now, when we say using algebra techniques, what that means is that I want to go through and I can use all the properties of equality here that we haven't been using in the previous sections. Because I do know in this case that these things are equal. I want to know when this 2 cosine squared x minus 1 is actually equal to 0. And in this case, I want to find all the solutions from 0 degrees to 360 degrees. Well, what I'm going to do in this case is I'm literally going to solve for the trig function. So the first thing I'm going to do on this is I'm going to add 1. And when I add 1 to both sides, so I'll get 2 cosine squared x equals 1. I'll then divide by 2. And I'll get cosine squared x equals 1/2. Now, I do have to solve for cosine x, not cosine squared. So when I take the square root, I will get that cosine x equals plus or minus the square root of 1/2, which if you simplify that square root, it comes out to be plus or minus square root 2 over 2. And now I want to identify every degree measure angle that has between 0 and 360 degrees, that has a cosine value of positive or negative square root 2 over 2. Well, the first one that we come to is 45 degrees. The second one is 135 degrees. The third one, 225 degrees. And the fourth one, 315 degrees. Those would be the solutions to that particular problem. Now here's the next one that we have. I have 2 secant squared theta plus secant theta minus 1 equals 0. Now, one of the things I can do with this is I need to solve this one. And when I look at this, the first thing you should notice is that there are 1, 2, 3 terms. You'll notice that the power here is double the power on this one. The power on this one is 1, power is 2. This one right here is a quadratic form. Now, it looks a little bit different than the quadratic forms you dealt with before, but I can still do the same thing I did before when we dealt with these back at the beginning of the year. I can make a substitution. I can make a u substitution. Now, as we talked about then, if you feel comfortable factoring these without making that substitution, that's fine. I'm going to make it right now. In this case, I'm going to let u equal the secant of theta. And so this will become 2u squared plus u minus 1. So I factor that. I'll have a 2u and a u. And it will be plus 1 here and minus 1 in terms of factoring it. At this point, you might have to try it. I happen to know this one, maybe you had this one right away. If not, it's trial and error. See what you can come up with on it. So I have to go back to this one, and it is going to be then factor as 2 secant of x minus 1 times secant x plus 1. And that equals 0. So to solve this one, I'm going to set each factor equal to 0 and solve for the trig function. In the first one, I get 2 secant of x minus 1 equals 0. When I solve for secant, I'm going to get secant of x equals 1/2. In the next one, I get secant of x plus 1 equals 0, and I get secant of x equals negative 1. Now, let's take a look at this first one that I came up with. In that situation, secant x equals 1/2. That right there, you should be very happy right now when you see this. And the reason is because you know that secant cannot possibly equal 1/2. So therefore, for this one, that's not possible and there's no solution here. The other part though, this one here, there is a solution. Secant of x equals negative 1. Well, that's going to happen if we think about the unit circle. Remember, secant is the reciprocal of cosine. So at the same time, I could say that cosine of x equals negative 1 as well. Now, if I'm working in degrees, I'll keep this one in degrees. Cosine of x is negative 1 at 180 degrees. So that would happen when x equals 180 degrees. And if I'm going from 0 to 360 degrees, like I have up above, that would be your only solution. So in this case, for this particular problem, my only solution is 180 degrees. Here's one using identities. I've already written this one out. What we have is, in this problem, we have 4 cosine squared x minus 4 sine x equals 5. We want to solve it for all real numbers. So we'll deal with that one, finish that one up in a second. So what I'm going to do on this one, right away, the fact that I have 2 different trig functions here tells me there's a problem because I don't have the multiplication to help me out there. So what I'm going to do is I'm going to change everything. Since I have a cosine squared and sine, since that's a sine to the first and that's a cosine squared, I'm actually going to change the cosine squared into, using the Pythagorean identity, I'm going to replace cosine squared with the 1 minus sine squared x. And so I have 4 times the quantity 1 minus sine squared x minus 4 sine x equals 5. Distributing that 4, I get 4 minus 4 sine squared x minus 4 sine x equals 5. Now at this point, I want to get everything to one side because right away, the first thing I notice on here is I'm dealing now with a sine squared and a sine x. I know I'm going to be factoring this thing. So what I'm going to do on this one is I'm going to pull everything over to one side, and I'm choosing to move everything over to the right-hand side. So I'm going to have a 0 here. And the reason I'm doing that is because that's a negative there. I want to deal with just positive coefficient on the squared variables, on the sine squared term. So in this case, when I bring everything over, I get 4 sine squared x plus 4 sine x plus 1, and that equals 0. Now, I can factor this again. Now, I can do the u substitution. I just went, if you want to, you can pause it, do that u substitution. But it will factor as 2 sine x plus 1 times 2 sine x plus 1. In other words, this right here is a perfect binomial square. So to solve it, I'm just letting 2 sine x plus 1 equals 0. So I get 2 sine x equals negative 1. Sine x equals negative 1/2. Now, I want to identify all real numbers where this happens. So what I have to do is look at the unit circle, identify what angles have a sine value of negative 1/2 on the unit circle, and remember to just add the plus 2 pi n. So in this case, one place where that happens is going to be 7, where x equals 7 pi over 6 plus that 2 pi n. Or the other place, x equals 11 pi over 6 plus the 2 pi n. Let's take a look at this last one. We're going to deal with this as tangent squared x minus tan x minus 2 equals 0, and I'm going to solve it from 0 to 360 degrees. This time I'm choosing to use the u substitution. So when I went through and did this one, I let u equal tangent x, so that became u squared minus u minus 2. And that will then factor as u minus 2 times u plus 1. When I go through, replace the u with tangent x, I get tan x minus 2 times tan x plus 1 equals 0. Setting each factor equal to 0 and solving for the trig function, I get tangent of x equals 2 and tan x equals negative 1. And I want to find all the solutions from 0 to 360 degrees. Now we're going to deal with the tan x equals negative 1 first, because that's one that we've dealt with already. Tan x equals negative 1. I want to find the solutions from 0 to 360 degrees. And I know one of those comes out to equal, that's going to happen when x equals 135 degrees. That gives me one. That's the in quadrant 2. And to identify the next one, I can either go through and look at the unit circle, or remember that I can just add the period. The period on tangent is 180 degrees. So my other solution is going to be when x equals 135 degrees plus 180 degrees, which comes out to be 315 degrees. So that's a 15 right there. So 315 degrees, and those would be my solutions on that side. The other side was a little bit different. Tan x equals 2. Well, in this case, I know then that x is equal to the inverse tangent of 2. And so to do this one, I now need to go and pull out my calculator. And what I'm going to do is make sure your calculator, because we are working from 0 to 360 degrees, so I want these answers to be in degrees. I pull out the calculator and I'm going to do the inverse tangent of 2. I plug that in my calculator and I find out that x is equal to 63.4349 blah 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 degrees. Well, the book is going to tell you to round it to 2 decimal places, so we'll do that. 63.43 degrees. We do want to identify there is another one here. We add 180 to that, so x equals 63.43 degrees plus 180 degrees. And I find out then that x is also equal to 243.43 degrees. So in this case, I have 4 solutions: 63.43 degrees, 243.43 degrees, 135 degrees, and 315 degrees. This now concludes the video that I have on solving the trig functions. I went through, you saw a lot of different examples. Please go back through and double check, make sure you're comfortable with those calculations. If not, be sure to ask about them. We will do some more examples in class as well. So with that, have yourself a good evening, and I'll see you in our next class.